You wake up early, walk out to your car while the sky is barely light, coffee still hot in your hand. You plug in, and 5 minutes later the battery is at 100%. Not half an hour, not an hour, 5 minutes. You pull out of the driveway and just drive, all the way from Los Angeles to Seattle, over 1,100 miles without ever stopping to charge. Sounds like something out of a movie, right? That's exactly what most people thought, at least until recently. Because for years, the general belief was that solid-state batteries, the technology the industry has long called its holy grail, were still 10 or more years away from ever reaching real consumers. Too many problems, too many walls, too many big promises that quietly faded into nothing. Every year, analysts kept pushing the target further out. In the year before last, they said 2035. Last year, they moved it to 2030. Eventually, the industry just stopped taking the big announcements seriously. Then Toyota said something. Not at some flashy launch event with dramatic lighting and a live stream pulling in millions of viewers. Just a closed-door meeting in Toyota City, Japan. A few dozen senior executives, a handful of carefully selected investors, and engineers who had spent a full decade working completely out of the spotlight. No theatrics, no special effects, just numbers. And those numbers stopped the entire auto industry cold. 1,200 miles on a single charge, a full charge in under 5 minutes. No cobalt, no nickel, no dependence on the kind of geopolitical supply chains that keep energy executives up at night. And most critically, not a lab prototype. This is a battery that has already been driven on real roads in real conditions across 4 continents. Within 72 hours of the information leaking out, more than $46 billion was wiped from the combined market value of traditional automakers and battery manufacturers. Electric vehicle startups that had been riding waves of hype suddenly looked fragile. The biggest names in Detroit and Europe quietly called emergency meetings behind closed doors. And the question everyone is now asking isn't whether solid-state batteries are possible anymore. The question is, how did Toyota manage to pull this off without anyone seeing it coming? Is this genuinely the turning point that reshapes the entire game, or is it just another round of hype waiting to fall apart? And if Toyota really delivers, what does that actually mean for the rest of the electric vehicle world and for the money in your pocket? That's what we're going to break down today, piece by piece. Before we get deeper into the story, if you enjoy this kind of technology and EV analysis content, go ahead and hit subscribe right now. We put out new videos every week, and this is a story you really don't want to fall behind on. How long has the lithium cage kept us trapped? To fully understand why Toyota's announcement landed like an earthquake, we need to rewind a little. Not decades back, just about 30 years. In 1991, Sony launched the first commercially available lithium-ion battery. At the time, it felt like a genuine miracle, compact, rechargeable, and storing more energy per kilogram than anything that had existed before. Within a decade, it was powering laptops, mobile phones, cameras, and eventually electric cars. Tesla, Nissan, GM, and then basically everyone else built their futures on that foundation. Massive factories went up. Supply chains stretched from cobalt mines in the Congo all the way to production plants in South Korea and China, and then back to the United States. A global industrial ecosystem worth hundreds of billions of dollars was built entirely around one battery chemistry. But lithium-ion was never perfect. After 30 years of use, its limitations are becoming harder to ignore. The first issue is energy density. The best lithium-ion batteries available today store roughly 250 watt-hours per kilogram. That might sound like a technical number, but the real-world consequence is straightforward. To give an electric car a range of 300 to 400 miles, you need a battery pack that can weigh close to 1,000 pounds or more. That's why most electric vehicles today are significantly heavier than a comparable gasoline car, sometimes by 500 to 1,500 pounds. All of that extra weight affects how the car feels to drive, how much energy it actually consumes, and ultimately how much it costs to build. The second problem is charging time. Even with the most advanced fast-charging hardware currently available, like 350 kilowatt DC stations, you're still looking at roughly 20 to 30 minutes to go from 20% to 80% under ideal conditions. In cold weather, extreme heat, or with an older battery pack, that gets significantly worse. Compared to a 3-minute stop at a gas station, that gap is still large enough to keep a lot of drivers from making the switch. Third, and this is something that doesn't get nearly enough attention, is safety. Lithium-ion batteries use a liquid electrolyte that is flammable. If the battery is punctured, overheated, or seriously damaged in a crash, it can ignite through a chain reaction called thermal runaway, a fire that ordinary water cannot extinguish and that can completely consume a vehicle in just minutes. These fires don't just destroy property, they erode trust in electric vehicles in a way that's very difficult to rebuild. And fourth is the raw material problem. Cobalt, a key component in most lithium-ion cathodes, is largely sourced from the Democratic Republic of the Congo under conditions that have been widely documented as exploitative and in some cases involving child labor. Lithium primarily comes from South America and Australia. Nickel comes from Indonesia and Russia. These are supply chains that run through politically volatile regions, and any disruption sends shockwaves through the entire EV industry. This is the lithium cage. The industry has been living inside it for 30 years. Nobody wanted to stay locked in forever. The problem was that nobody knew where the key was. Until now. Inside Toyota's secret laboratory, Toyota is not the name most people associate with bold technological leaps. For years, as Tesla was reshaping the world's idea of what a car could be, and as GM and Ford were committing billions to their electric futures, Toyota appeared to be watching from the sidelines, still selling hybrids, still expressing doubts about whether pure electric vehicles were ready for the mainstream. Critics called it the stubbornness of an old-world company refusing to accept change. But that wasn't stubbornness. That was camouflage. While every spotlight in the industry was trained on Tesla and a wave of well-funded EV startups, Toyota was quietly running one of the largest battery research programs in automotive history. Thousands of engineers, billions of dollars, and one clear objective: not to make lithium-ion better, but to replace it entirely. The technology they committed to was the solid-state battery. The underlying concept isn't new. Scientists have understood for a long time that replacing the liquid electrolyte in a lithium-ion battery with a solid material would immediately remove the fire risk, boost energy density, and enable much faster charging. The theory is elegant. The execution is extraordinarily difficult. The most persistent challenge with solid-state batteries has always been the interface, the microscopic contact zone between the solid electrolyte and the electrodes. At the atomic level, solid materials expand and contract with temperature changes in inconsistent ways. After hundreds of charge and discharge cycles, tiny fractures form at that interface and the battery gradually degrades. This is exactly where every major attempt to commercialize solid-state batteries over the past 2 decades has broken down. Dozens of companies and research institutions tried, and all of them hit the same wall. Toyota didn't solve that problem by refining existing materials. They sidestepped it entirely by developing something new, a proprietary ceramic polymer matrix that blends the structural resilience of advanced ceramics with the flexibility of organic polymers. The result is a solid electrolyte that can survive thousands of expansion and contraction cycles without cracking, without degrading, and without losing its ability to conduct ions efficiently. That is the bedrock of everything that follows. On top of that, Toyota introduced a second breakthrough in the form of a graphene-infused anode. Standard lithium-ion anodes are typically made from graphite. During charging, lithium ions migrate into the anode and accumulate there. Over time, they begin forming tiny metallic structures called dendrites, almost like microscopic branches growing inside the battery. Dendrites are the primary failure mechanism in lithium-ion technology. They reduce capacity, cause internal short circuits, and in serious cases, trigger thermal runaway. Toyota's graphene anode almost completely eliminates dendrite formation, not reduces it. nearly eliminates it. In internal testing, cells built this way endured more than 2,500 full charge and discharge cycles while losing less than 8% of their original capacity. In practical terms, that means a car with this battery could cover over 1 million miles before the driver notices any meaningful drop in range. Put both breakthroughs together and the energy density jumps from around 250 watt-hours per kilogram, the current ceiling for lithium-ion, to nearly 450 watt-hours per kilogram. Close to double the energy in the same physical space at the same weight. On top of that, the pack is 30% lighter and 15% smaller than the battery units Toyota currently uses in its BZ lineup. But the most quietly significant number is the operating temperature. Even under aggressive fast charging or sustained heavy driving, the battery pack barely heats up at all. It runs cool, and no commercial lithium-ion pack on the market today can say the same. That detail, the ability to stay cool under pressure, is what unlocks everything else. Supercharging, super safety, and the production machine. When a battery can accept electricity quickly without building up damaging heat, you can charge it far more aggressively. That principle is what Toyota's Hypercharge 55 system is built on. To put the numbers in perspective, Tesla's V3 supercharger delivers around 250 kilowatts. The fastest stations currently deployed by Electrify America top out at 350 kilowatts. That is the current limit of what exists in the real world. Toyota's Hypercharge 55 system delivers 2.2 megawatts. That is 6 to 9 times more powerful than the strongest charging infrastructure available today. Through a new generation liquid-cooled cable, that level of current fills a Toyota solid-state pack from completely empty to completely full in under 5 minutes. Not from 20% to 80% the way automakers typically advertise charging speeds. From 0 to 100 in the time it takes you to use the restroom and grab a coffee. The obvious question is what that does to the electrical grid. If hundreds of cars are simultaneously drawing 2.2 megawatts, local infrastructure would collapse. Toyota has addressed this directly. Each Hypercharge station is paired with an on-site energy storage unit, essentially a large solid-state battery bank that charges slowly and continuously from the grid throughout the day and then releases that stored energy rapidly when a vehicle plugs in. From the grid's perspective, it never sees the spike. It sees a steady, manageable draw that goes on around the clock. The surge is absorbed and released by the station's own storage, not pulled directly from the network. It's a clean solution that removes one of the most technically grounded objections to ultra-fast charging. On the safety side, Toyota has turned what was once a liability into a genuine competitive edge. During crash testing, when the solid-state battery pack was punctured, it didn't catch fire. It didn't explode. It didn't even get dangerously hot. It simply stayed intact. In the most extreme fire simulations run under Japanese safety standards, Toyota's pack released less than 10% of the heat generated by a conventional lithium-ion battery under the same conditions. That isn't an incremental improvement. That's a fundamentally different category of risk. Beyond the battery chemistry itself, Toyota has integrated the pack directly into the vehicle's structural frame through what they call cell-to-frame architecture. Rather than sitting as a separate module bolted beneath the floor, the battery becomes part of the car's skeleton. That reduces weight, increases rigidity, and provides an additional layer of crash protection. The result is a vehicle that is 28% lighter than the current RAV4 while being structurally stronger and safer. None of that matters commercially, though, unless the technology can be manufactured at meaningful scale and at a price that real buyers can afford. This is where Toyota's story takes its most important turn. Right now, at the Motomachi plant in Japan, 2 fully automated solid-state production lines are already operating. Not a pilot program, not a controlled experiment. Running production. Initial output stands at 250,000 battery packs per year with a yield rate of 91%, at a time when most competitors in early trials struggle to break 70%. The key to that performance is automation. Ultra-thin ceramic electrolyte sheets are handled entirely by robotics inside sealed, moisture-free environments with AI-driven quality control monitoring every layer at the micrometer level. Labor cost per pack has dropped 60%. Production speed has doubled. Human error has been reduced to near zero. In Thailand, a new gigafactory is being built from the ground up with a single purpose: solid-state battery production at global scale. No legacy lithium-ion lines to phase out. No hybrid infrastructure to work around. Everything designed from scratch for this technology. Toyota's stated target is to have 80% of all solid-state components produced domestically by 2027, creating a self-sufficient supply chain that doesn't depend on politically unstable mineral exports. The vehicle designed to run on this platform already has a name: the Toyota X1. Not a budget hatchback, not a niche performance car. An SUV built from the ground up around solid-state architecture. More than 1,200 miles of range, a full charge in 5 minutes, a starting price under $30,000. And thanks to cell-to-frame integration, lighter, stronger, and safer than anything else on the market. Inside Toyota, there are people who genuinely believe the X1 will outsell the Corolla and become the best-selling model in the company's history. That might sound like corporate enthusiasm, but when you line up the numbers, it's not hard to follow the logic. What Toyota isn't telling you. At this point, you're probably thinking it all sounds a little too clean. So where are the problems? Fair question. And the honest answer is there are several things that still need independent verification. First, that 1,200-mile figure comes from controlled test conditions, not from everyday drivers in the real world. In practice, most automakers see real-world range fall 15% to 25% below official figures depending on driving style, temperature, and how the car is used. Toyota has acknowledged that under typical mixed American driving conditions, the real number may land closer to 958 miles. Still a number that would reshape the industry, but not 1,200. Second, 250,000 battery packs per year is a meaningful output for a new technology, but it's a drop in the ocean compared to Toyota's global sales volume of roughly 10 million vehicles per year. The Thailand Gigafactory will change that, but scaling a brand new manufacturing process always brings unexpected complications, from sourcing specialized ceramic materials to finding enough skilled technical workers to managing the learning curve of a production system that has no real precedent. Third, the $30,000 price point for the X1 has not been officially confirmed. It originates from internal sources and leaked documents, not a formal announcement. Ceramic electrolyte manufacturing at large scale is still more expensive than conventional liquid electrolyte production. Toyota believes costs will come down as volume increases and automation improves, but that remains a projection rather than a proven outcome. And fourth, the long-term real-world durability of the battery hasn't been verified by any independent third party. Toyota's internal testing shows 2,500 cycles with less than 8% capacity loss, but internal testing environments are always more controlled than actual use. How the battery holds up against real drivers with varied charging habits, exposure to extreme climates, and years of irregular use is a question that only time and independent data can answer. None of this is a reason to dismiss what Toyota has announced, but honest analysis requires seeing both sides clearly. The EV industry has already been through too many cycles of massive excitement followed by much slower and messier reality. Silicon anode batteries, sodium-ion cells, affordable long-range vehicles. Every time, the gap between announcement and availability turned out to be larger than anyone anticipated. Toyota has a stronger track record than most when it comes to actually delivering technology from the lab to the road. The Prius debuted in 1997 and is still going, but the hybrid transition was built on lithium-ion chemistry that already had a proven commercial track record. Solid state is a categorically bigger leap, and that is exactly what makes the race ahead so intense. Where the real battery war is happening, you can't talk about Toyota's breakthrough without looking at the broader landscape, because this is not a two-player game. In China, CATL, the world's largest battery manufacturer with more than 37% of the global EV battery market, already has its own solid-state program targeting commercialization by 2027. CATL's advantages are formidable: unmatched manufacturing scale, deep supplier relationships with automakers across China, Europe, and increasingly the US, and a structural cost advantage that comes from lower engineering labor costs and near total control over the upstream raw material supply chain. Their weakness is that their current architecture still relies on an NMC cathode, meaning even if they move to a solid electrolyte, they remain dependent on cobalt and nickel. Toyota has eliminated both. In South Korea, Samsung SDI has partnered with Stellantis to develop its own solid-state technology. Samsung has deep materials expertise and decades of consumer battery experience, but their program is still at small-scale testing and nowhere near production ready. In the US, QuantumScape, the solid-state startup backed by Volkswagen and Microsoft, has announced breakthroughs on multiple occasions and missed its timelines just as many times. The stock has dropped more than 80% from its peak. Solid Power, working with BMW and Ford, remains at the pilot stage. What sets Toyota apart from the startup world isn't just the technology, it's the infrastructure. Toyota doesn't need to raise capital through an IPO. It doesn't have venture investors expecting results every quarter. It has $250 billion in annual revenue, 7 decades of manufacturing experience, and hybrid production lines that have been refined over more than 20 years. That kind of industrial foundation is not something you can build in a boardroom. Meanwhile, GM, Ford, and Stellantis are in a genuinely uncomfortable position. They've committed tens of billions to next-generation lithium-ion factories. GM's Ultium platform, Ford's Blue Oval City. These are not investments you can reverse overnight, but if Toyota scales solid-state successfully, those factories risk becoming stranded assets before they've even hit full capacity. That's why Detroit's initial response to Toyota's announcement wasn't a public statement. It was silence, then closed-door meetings. Volkswagen, which had declared solid-state batteries its #1 strategic priority while watching its own timeline slip repeatedly, now has to confront the possibility that its roadmap looks like a relic from a different era. The race hasn't ended. It's just jumped to a speed that most of the participants weren't ready for. If Toyota is right, how does the world change? Let's start with the most personal level. You. If the X1 launches with a real-world range approaching 1,000 miles and a price under $30,000, that puts it below the base Tesla Model 3 at nearly 3 times the range. Range anxiety, the single biggest psychological barrier holding most Americans back from going electric, evaporates. Charging anxiety disappears. Battery fire concerns disappear. According to J.D. Power survey data, the top 3 things stopping American consumers from buying EVs are range, charging time, and price. If Toyota addresses all 3 simultaneously, the EV market doesn't just grow steadily, it surges. But the implications reach far beyond the automobile. Toyota has stated clearly that by 2026, the same solid-state technology will extend into home energy storage. Consider what that means. Pair rooftop solar with a Toyota solid-state home battery, and you could store enough energy to run your household for close to 2 full days without touching the grid, compared to less than a day with current lithium-ion storage. For families in rural areas, in storm-prone states like Texas or Florida, where grid outages are a regular reality, or in high electricity cost markets like California, that could translate into genuine energy independence. At a larger scale, Toyota is exploring industrial storage using the same architecture. Grid-scale solid-state battery farms would be lighter, safer, and designed to last twice as long as the lithium-ion installations being deployed today. That makes wind and solar genuinely more reliable, because the fundamental challenge with renewable energy has never been generating the electricity. It's always been storing it for when the sun goes down and the wind stops. There's also an emerging aviation angle. Toyota's aviation division is evaluating ceramic solid-state versions for next-generation drone systems and high-altitude platform aircraft, where the ratio of energy to weight is not just a performance metric, but a question of whether the mission is even possible. If solid-state energy density holds stable at 450 watt-hours per kilogram over long operational cycles, medium-range electric aircraft starts to look like a real engineering proposition rather than a distant aspiration. There will be a major geopolitical shift in raw materials as well. The cobalt market, dominated largely by Congo and controlled significantly through Chinese downstream processing, will face serious structural pressure if cobalt-free solid-state batteries scale to the mainstream. The same applies to nickel and, to a lesser degree, lithium. Countries that have built major export revenue around these materials will need to reckon with that. Meanwhile, Japan, a nation with almost no significant natural resources of its own, will hold a new kind of geopolitical leverage, proprietary technology. And if Toyota ultimately scales solid-state production into the tens of millions of units annually, it stops being just a car company. It becomes one of the most important energy suppliers on the planet, the kind of role that used to belong to names like ExxonMobil, BP, or Saudi Aramco. So where does this all leave us? For decades, the EV industry has been operating inside a lithium cage. The technology was good enough to start a revolution, but not powerful enough to complete one. Short range, slow charging, hidden fire risks, and a supply chain running through some of the most geopolitically fragile corners of the world. Together, these kept electric vehicles from becoming a genuine mass-market choice for most people. Toyota didn't try to break through that wall. They built a completely different road around it. A proprietary ceramic polymer electrolyte that eliminates the interface cracking problem. A graphene anode that virtually removes dendrite formation. A 2.2 megawatt charging system paired with on-site storage so the grid never takes the hit. Automated production lines running at yield rates no competitor has matched. No cobalt, no nickel, and a domestic supply chain designed for long-term self-sufficiency. And a car priced under $30,000 intended to bring this technology to tens of millions of people. That is the complete picture, if everything unfolds the way Toyota has planned. But, and this matters if you want to think about it clearly, rather than just getting swept up in the excitement, the history of EV technology has delivered one expensive lesson repeatedly. The distance between something that works in the lab and something that millions of people are driving off dealership lots is always larger than it looks on paper. Manufacturing at scale always surfaces problems that controlled testing never caught. Real costs tend to run higher than early-stage projections, and consumers don't always respond to technology the way engineers expect them to. Toyota understands this better than almost anyone. They lived it with the Prius, with the Mirai, and with multiple generations of hybrid technology. And the fact that they're approaching this quietly, running real production lines and testing on 4 continents before calling a press conference, is probably the strongest signal that this isn't ordinary hype. But we still have to wait. The next few years are the real test. Does the X1 launch on time? Does real-world range come anywhere near the announced figures? Does the price actually land under $30,000? And after 3 years, after 5 years of actual daily use by real people in real conditions, does the battery hold up the way Toyota says it will? No press release can answer that. No engineering presentation can answer it. No YouTube video can answer it. Only reality can. But one thing is already settled right now. The nature of the race has changed. It's no longer a debate about whether solid-state batteries are achievable. It's about who masters them first, at what scale and under what conditions. And Toyota, against almost every prediction made over the past decade, is currently out in front by a significant margin. That lead can change. In technology, leads always can. But right now, today, this year, Toyota is rewriting the rules of an industry that thought it had already figured out how the game was played. So what do you think? Do you believe Toyota has genuinely pulled the future into the present, or are you still skeptical about some of those numbers? Drop your thoughts in the comments. We read everything and we genuinely want to know where you stand. If this video was worth your time, hit like so more people can find it. And if you want to stay with this story as it develops, subscribe and turn on notifications. We'll keep following every development because we're really only at the beginning of this chapter.